So perfect. So I think we're about ready to start. Victoria, as I said, I will mute myself and turn my camera off. When I put my camera back on, that just says you're coming up on the 20 minutes. For all our participants, again, if you have questions, please pop them in the Q&A. You can upvote them as well if you'd like, and then we'll try to answer those at the end. But let me first introduce our next speaker. So this is Vittoria Laghi. She's a junior assistant professor at the University of Bologna in Italy, lecturer at Massachusetts Institute of Technology, and visiting researcher at TU Braunschweig in Germany, as if that's not enough things to be doing. So her research is mainly focused on structural applications of steel 3D printing technologies, particular interest in wire and arc additive manufacturing. So I think at that point, I'm going to hand over to Victoria to talk to us about wire arc additive manufacturing.
Thank you, Candice. So good morning or good evening, everyone, wherever you are located in the world at this moment. So, and thank you also for the presentation. So I'll just quickly present the work that I'm going to share with you. It's my research on how to best apply metal 3D printing, and in particular, wire and arc additive manufacturing for large-scale applications and in construction. So I'll just move very quickly. This is something that was already by Candice, so I'll just move forward. But just to say that my background is in structural design, so I'm a structural engineer, and from my PhD on, I've just focused my research on how to best apply steel 3D printing in construction. But not just that. I come from study of large-scale 3D printing for construction, but also earthquake-resistant design and everything that concerns efficient applications for structural design. So a little bit of an overview on metal 3D printing in construction. So over the past decade, there has been an increased interest in how to best apply this technology for construction. But at the beginning, it was just applied to very few architectural pieces, and mainly in small connections and small pieces of the whole structure. And over the past 5 years also, or I would say, there has been an increasing interest and an increased scale of the applications for construction with the use of wire and arc additive manufacturing that allowed to, again, to increase the scale of the printed element up to the entire scale of the whole footbridge, as for the case of the MX3D bridge located in Amsterdam. But what is wire and arc additive manufacturing? So it's a weld-based metal 3D printing technique that uses off-the-shelf welding equipment mounted on top of a robotic arm. So this allows to actually produce and print steel pieces or metal pieces up to a few meters of width and a couple of meters of height. There are two printing techniques that we know of. So one, it's called the continuous printing, and it's like the traditional layer by layer 3D printing that creates shells, elements, solid elements. Whereas the dot by dot printing is the one that I'm going to focus my presentation a little bit more on. And it consists on different drops of metal to create bars and lattice structures. Of course, there are many pros and cons as for everything, and especially for additive manufacturing. But in this case, for metal additive manufacturing and construction, this is like the advantage for wire and arc of having a fast production and ideally no geometrical constraints, as it's not located within a box. So you can actually increase the size of the printed part up to, as I said, a few meters, and the result is actually quite resistant, so it's good for structural applications. But the open issues that still needs to be tackled are the lack of proper material and mechanical characterization of the printed piece, and lack of current standard design procedures to efficiently apply that for construction. So I personally see a huge potential at a longer distance, let's say, of applications of wire and arc additive manufacturing and construction. And this is the reason is to provide efficient geometries and efficient designs. So with this freedom of being able to print ideally whatever geometry you want, you can actually severely reduce the material use and clearly optimize the geometry for the use that we want to have. And this can also, of course, at a longer approach, also reduce the environmental impact of the construction like the construction sector, which is, of course, a topic which is of high importance, especially over the last few years. But this also results in the need of having a multidisciplinary approach when it comes to applying metal 3D printing in construction. So it's not just the design phase, but it's also the testing and verification that's behind it, the fabrication issues, the robotics behind it. So it's all these different pieces of a puzzle that need to be put together. So when it comes to draw new guidelines, so I'm sure you might not be fully familiar with the structural design codes, but conventionally speaking, we have design values for resistance that we have in our guidelines, either that it comes from the National Building Code, the International Building Code, or whatsoever. But when it comes to new materials, we do not have that. So we need to come up with something new. So what it's usually been done is to have advanced numerical modeling. So what it's called digital twin or digital shadow, design assisted by testing. So you need to carry out many tests for every new project that concerns either new guidelines, new designs, or new materials. But that's not really feasible for large scale of applications in construction. Like if we want to increase the application in construction of this new material, we need to come up with new solutions. So what I've been studying over the past years is to try to have different information, different data that would populate a new design approach, that it's based from conventional design approach, but it's tailored to still 3D printing. A little bit of my previous work on WAAM. So of course we started from the basics. So we wanted to test stainless steel material. We started with stainless steel. We started with continuous layer by layer printing, and we tested on different levels. So tensile test for the mechanical properties, but also microstructural analysis and so on and so forth. What we came up with was that the material, the printed stainless steel, resulted to be highly anisotropic and in particular orthotropic. So the mechanical property, both at the elastic and post-elastic range, were severely affected by the relative printing direction of the piece. So this was in conjunction with the study at the microstructure, because at the micro scale, we found out that the crystals orientation were actually perpendicular to the printing layers. So this allowed us to create a new orthotropic material model for the stainless steel to be used in the future for design. Not only that, as I said, the geometrical characterization was also another crucial point that we need to tackle. So the as printed part have internal surface roughness, lack of straightness, different thickness, variation of the thickness or of the diameter. So we need to, of course, account for that, because for large scale application, we do not expect to have post-process. So we expect our piece to be as built, as printed, therefore rough. All these pieces were put together to create new structural design guidelines, the first guidelines for WAAM stainless steel for construction. So we calibrated ad hoc design values and partial safety factors based on the experimental data that we collected before. We also played around with the design. So we created new design solutions, new efficient structural elements based on what? Based on, of course, optimization studies, but also basic principles of structural design. But we also wanted to tackle the issues of WAAM itself. So the orthotropic nature of the material and also the fabrication issues and constraints. Last but not least, we also developed an idea solution along with the robotic department at the University of Bologna, Italy, for an integrated mobile 3D printed system. The idea is to have a mobile 3D printer that is able to move along the element while 3D printing on it. And it's currently under patent protection. These are just few of the related projects that that I've worked with, and I would like to highlight the Address for Future, which is a European project to create new courses for students and professionals related and tailored for additive manufacturing at different scales, and the TRR 277, which is a collaborative research center on additive manufacturing for construction in a joint work between TU Braunschweig and TU Munich in Germany. Now moving to the core of my presentation, so dot by dot printing for lattice structures. Dot by dot printing is, again, as I said, a different type of WAAM printing strategy, which creates bars, rebars, and lattice structures and die-grid systems, pointing drops of molten metal one on top of the other. So these allow to create lattice structures and bars at different scales. Of course, the issues when it comes to this type of printing is to consider the influence of the build angle, the geometrical irregularities as well, and of course, again, the anisotropy of the mechanical properties. The advantages are the possibility to realize highly efficient lattice elements, and we're going to see that in a minute. So the idea is to move from the conventionally extruded poles or hollow section metal elements to the lattice element. This is actually an algorithm that is currently under patent protection in Italy, but we developed this algorithm that allows to have for slender elements the same structural behavior by changing the cross section. So from an extruded hollow cross section to a lattice cross section that could be printed with WAAM. This will have the same material, like the same structural behavior, but with up to 90% reduction in material use. This, however, has as drawback, of course, a long printing time that needs to be optimized. So at the mesoscale, we want to investigate and apply lattice, the principle of lattice elements, but at the scale of the single structural element. So we know that lattice elements and lattice material is actually something quite used at the micro scale for like the high stiffness and the reduced material use, but also at the macro scale, because as a structural designer, I know very well, and I've been studying for a while, truss elements. So truss elements are actually something that have the same principle as for the lattice elements, if you think about it, because they have been used for high stiffness and reduced material use, so lightweight structures with high stiffness. But we want to actually combine these two and go at the mesoscale, so at the scale of the single structural element, either a column, a pillar, or a beam. And I started this research in 2018 at the MX3D, where I was an intern for my PhD. But then I moved towards from this idea that we're going to see as a case study in a minute, up to the 2022, where I actually presented an Italian patent of the algorithm, the solution for lattice elements. So a little bit of the experimental test. Again, as I said, this of course is we needed to start from the basics. So we started from the single boss, printed at different inclinations to see the influence of the build angle on the geometrical and mechanical properties of this single boss composing the lattice structure, the lattice element. So we started from the geometrical characterization. So we studied the lack of straightness and the variation of the diameter of these bars based on the build angle. And we saw that the higher the build angle, so increasing the build angle will have a detrimental effect on the geometrical part. So meaning that with higher build angle, we have also higher eccentricity and higher lack of straightness, but also reduce the material properties. So this also has a detrimental effect on the material, not the mechanical properties as well, both at the elastic and post-elastic range that we need to tackle, of course, in the design phase. So just to see a little bit of the case studies on this application for construction. So the first one, as I said, was developed at MX3D in 2018 while I was an intern for my PhD. So the first idea was really to come up with a die-grid column. So this was a half-scale die-grid column, so it's 2 meters high, and it was designed to sustain a certain load. So it was like meant to be for structural applications, but also to already tackle the fabrication constraints. So we want to have a certain maximum angle of the single bars and to provide a shape that could be efficiently produced as well. Then I moved my research at the TU Braunschweig in Germany in 2021, and we started to print back again these with dot by dot. So from the bars that you see on the left-hand side till the single cells up to scaled columns and elements. The end of my research there at TU Braunschweig resulted in a proof of concept of the base of a pillar. So we designed a pillar that was supposed to be 12 meters in height. And of course, this is just a proof of concept. So we started to print just the base of this. But of course, like it's just the idea of be at a very high scale, at a very large scale of application for construction. And this is an in-field die grid, meaning that it's a 3D die grid. It's die grid not just of the exterior, but also inside of it. So to increase the stiffness while still having and maintaining a reduced material use. Last but not least, this is something that I'm very passionate about, and it's a case study that we developed at TU Braunschweig as well, and it's called FLOWALL. So it's the first time that we combined two different additive manufacturing techniques for large-scale applications. So in this case, we have the case study of protective structures, coastline protective structures that can be adapted for the environmental use. So they can be adaptive for both the coastline itself and also the wave effect coming from the sea level. We wanted to create a wall that could be adapted so that the shape could actually adapt to the coastline and the wave. And for that reason, we created adapted and freeform rebar in WAAM that was then covered with shotcrete at the second stage. So this is the first time that we apply WAAM as reinforcement and shotcrete, so 3D printed concrete for the matrix itself. And this product, this proof of concept was also recently awarded with the 3D Pioneers Challenge, the special mention by Autodesk, and also the Iconic Award in Germany. So what's next? So this is just a very quick overview of some of the possible applications of metal 3D printing in construction, and especially WAAM to realize lattice structural elements and efficient elements for a new generation of low impact construction. We started from the characterization of the geometrical and mechanical properties, but then we want to move towards the a new computational design and fabrication system for large-scale elements that could sustain the structural requirements while still allowing the fabricability, so to allow also for the fabrication issues. The future perspective can apply mobile 3D printing solution to also increase the digitalization in the fabrication and in the construction system. And who knows, these solutions can also open unexplored possibilities in scenarios that also not involve humans. So who knows, maybe beyond our Earth. This is just a list of significant publications that I have. I've also put in my profile, my ResearchGate profile. So in case you want to download some of the articles or just send me a message, and I will be more than happy to share that with you. And thank you for the attention.
Thank you very much for that. Nice to see the kind of large scale things being talked about as well. I don't know if you can see on your screen, there's a few claps, like virtual claps on the screen to celebrate the end of your presentation.
Thank you.
So we have a question in the chat. I love this. The question in the chat starts with, "This is so cool." That's great. I agree. How close are these structures to being installed in construction applications? And in particular, what kind of qualification is needed for that? Can you maybe comment on that side?
Yeah, so thank you for the question. That's very interesting, and thank you also for appreciate my presentation. So I just moved very quickly to the first slides, but actually there is the first steel footbridge that was entirely printed with these technologies, so with wire and arc additive manufacturing in full stainless steel, and it's currently located in Amsterdam city center. So this is actually the very first practical application of that that you can actually go there and walk by and see it, but also really just cross it. Um, so of course, there's still some work to be done. There are guidelines to be drawn and qualifications to, let's say, fix the mechanical properties and be able to predict the mechanical properties based on the printing process parameters that you are using. So this, I think, is one of the major issues that are quite common for different additive manufacturing materials and applications, because this is, I think, is like the crucial point on how to predict the behavior based on the different setup, the different printing setup, the different printing process, the parameters that you're using. And we are working on that. I'm personally very passionate about it, and that's also why I've done like a few publications and few studies on that, to really draw design values and guidelines and help also producers and industry at that level. So to help provide the clients with the design values and the strength values that they can use to safely use this material for construction. But not only that, the ASTM is currently working with working groups to create ad hoc guidelines for additive construction. So very recently they opened also to metal, because at the beginning they were first focused only on concrete 3D printing, but we all know that also metal is important for construction. So
yeah, wonderful. And nice to mention the ASTM and the standardization, because I think when I first started in additive, there wasn't any of it. It was just kind of everyone does what they feel like, and that. We have another question about materials there. So are there specific materials that work really well for this process? Are there others that don't? Is there work going on that?
Yeah. So we started with stainless steel because actually stainless steel works quite well. And I mean, the properties can be well predicted, even though it's one of the material that results in having the highest anisotropy. So the highest relative difference of the properties with respect to the printing direction. Carbon steel works also quite well and has reduced anisotropic behavior, which is good, because then we can predict an almost isotropic behavior of the material to be printed. Aluminium does not work super well, meaning that it's quite hard to 3D print it, but there's huge research going on that, because of course, like for aerospace applications and others, that's like a very nice application and a very nice material to use.
Yeah, because I was thinking about that actually when we talk about things for construction, that's great, but basically that could also mean anything big, right? Like large scale products.
That's true.
And I had a quick question for you, if that's okay, because you mentioned early on in your talk about this kind of lots of pieces to the puzzle of making it all work. And I know you've got some welding, you've got robotics and so on in there. How well does that work? Like, how seamless is it to actually get everything to work together? Or is it particularly, you're smiling, so I'm guessing it's a lot more complicated than it perhaps sounds.
Yes, it is. I mean, I really like the team effort. So I strongly believe that there shouldn't be just one person knowing all of it, but there should be like a team effort. So this interdisciplinary work in general, I think it really allows us to open up ourselves a little bit more to work together with other professionals that have like that specific skill that we maybe personally do not have. Like I personally am not a robotic expert, for example, nor a welding expert, but I can ask other people to help me out in that, and I can have like basic knowledge on that. But I think it's really important to create an interdisciplinary team to work together rather than try to know everything about that yourself.
Yeah, I think it would be a long time before any of us would be an expert on anything. On that note, then, are there other people that you think it would benefit to bring on board? Like, are there disciplines missing here? And you kind of thinking, oh, if only people from this area were interested, we could make the next big jump. We've got quite a few participants in this room who may have those skills, but what's missing from that kind of expertise, do you think, if anything?
Well, I personally think that, well, I come from research, so at a higher note, I would say that in general, the collaboration between industry and research should be a little bit more close, meaning that we work as researcher predicting or thinking what could be useful for the industrial applications, or for a wider audience. But what I would really love to hear about would be, from the industrial point of view, what they would need from us to do, and try to really have a closer collaboration in that sense. Because for the moment, I think that especially for these the specific technology, we have quite good knowledge from the research point of view, and the industrial interest is high, but I think we still need to communicate properly in order to really work together towards a wider application of this technology in construction. And this would be, I mean, it's not a specific discipline as you were asking, but I think it's more on a higher scale, like to really have, I think, more communication and more collaboration between industry and research, because usually industry works on a case study level. Research is more widespread, but at the same time, like, we can still find mutual interests to work on.
I think that's a perfect answer, and I think we've seen a bit of that through the talks this morning already, that actually that industry involvement, and it's kind of like making sure we don't run off and do research on the things that aren't interesting or whatever. So if there are any industrialists in the room listening, contact Vittoria with your ideas and she will make them happen.
Thank you.
Thank you very much, Vittoria. I'm going to send you back to the floor. Again, it sounds horribly rude to say it, but that's what we'll do. Thank you. That was a fascinating talk.